So we were working on circuit problems. We talked about two types of circuits or two types of combinations. One is series combination. Series combination is where two resistors are connected in series like this. So this R3 is in series with R4, and R1 is in series with R2. Okay, and also parallel combination. Parallel combination is you have a resistor like this and then a resistor like this. So these two are in parallel combination. Okay, or you can have another one also. So these are in parallel combination. And then sometimes you may have combination of series and parallel. So in this circuit, you have series circuit, and then these two are in parallel with this R5. Okay, so you can have combined parallel and series. So in this circuit, it's asking you to find an equivalent resistance of this entire resistors. What that means is you need to draw a single resistor that represents all of the resistors. In other words, if you were to replace all the 5 resistors by one resistor, then what would the value of that resistor be? Okay, so this E is electromotive force. It's not force, it's just misnomer. It's also called EMF. It's the potential difference of the battery when it is connected to some active circuit. Active circuit means when there is some flow of current. Okay, so EMF is called force, electromotive force, because it forces the current in the circuit. But it's not actually a force. It's not unit. Its unit is not Newton. Okay, so but these two are more or less same. So in this circuit, we want to find the equivalent resistance of this combination, and then find the current, these I's. Okay, so I can write this as combination of these two. So combination of these two would be whenever the resistors are in series, R equivalent of the two resistors in series is given by their sum. So R1 plus R2. So that is R1 is 6 and R2 is 4. So 10. So I can replace these two by 10 ohms. So this is 10. Okay, I can replace these two by its equivalent resistance. So the equivalent resistance for so let's call this for 1 and 2, for 3 and 4, so these are series in series. So R3 and R4 are combined to give you R3 is 5 ohms, R4 is 3 ohms. So the total would be 7 ohms. So I can replace these two by 7 ohms. Oh, sorry, 8. Okay, yeah, thank you. Okay, because of the problem, I'm having some trouble with adding. Okay, so the bottom one is as it is, R5. Okay, nothing changed. The upper one is we are replacing that by 8 ohms. And then everything else is as it is. Okay. And then now the next thing is for 8 ohm and R5. So those two are in parallel. We can now replace these two by their equivalent resistor. Their equivalent resistor, whenever they are in parallel, we use this formula. Okay, R equivalent is 1 over 8 ohms plus 1 over R5, which is 2 ohms. Okay. So you can use a calculator to do this math, or you can do a little bit of math here. So the common denominator is 8 ohm, least common denominator, and then 1 plus 4, 5 over 8. Now you need R equivalent, not 1 over R. So to get R equivalent, you need to do the reciprocal of on both sides. So 8 ohms flipping top and bottom, you get that. So 8 divided by 5 would be 1.6. 1.6 ohm. So I can replace these two by 1.6 ohms. Okay, so this is 1.6 ohms, and that's 10. Okay. Now I need to find the equivalent resistor for these two also. So these two are in series for 10 ohm and 1.6 ohm in series. In series, equivalent is just adding to the two resistors, 10 ohm plus 1.6 ohms. So adding that, you get 11.6 ohms. Okay, so that would be the equivalent resistor, whose value is 11.6. That's the answer for first question, first part. Second part is asking to find the current and potential difference through each of the resistors. So to find that, you use Ohm's law in the simplest one. So apply Ohm's law. We know the Ohm's law is given by delta V is equal to I over R, or sorry, I times R. Okay, delta V is already there in the circuit, and R is also there. So delta V, when the battery is exactly parallel to the resistor, the potential difference here would also be same. Okay, so the potential difference in a parallel circuit is always same. So that means the potential difference across this resistor would also be 14.5. So that means we can find the current through the resistor now. We know potential difference and R. So current would be, rearranging this equation, delta V over R. Delta V is 14.5. Okay. Again, just a reminder, when you have only one resistor and battery, the potential difference across the resistor would be same as that of the battery, which is not true if you have multiple resistors. Okay. In case of multiple resistors, like in this case, the potential difference here is 14.5, but the potential here would be different from that. Okay. So in this case, the potential difference would be split between these two, or distributed between these two. But if there is only one, then all the potential would be given to this resistor. So delta V is 14.5 and R is 11.6. Now just a reminder that if we are talking about a battery, then we call the potential difference as EMF, Okay, but if we are talking about the resistor, potential difference across the resistor, we just call it potential difference. We don't call it EMF. EMF is the term only used for the potential difference across the battery. Okay, for source, it's the potential difference across the source. So once we have that, now we can, all we need to do is we need to go backwards. Okay, so find the value of I. 14.5 divided by 11.6, that's 1.25 amperes. So the current in this circuit is 1.25 amperes. Now we need to go backwards, so go one step backward. So these two resistors are formed by combination of, this one is the combination of these two resistors. That means the current that is going through this resistor would be also the current through each of these resistors. Okay, so last time we talked about the rule: if the two resistors are in series or two or more, then the current going through each of the resistors would be same. Okay, so if I is the current going through this one, then the same current would go through this one, the same current would go through that one. So in the series combination, current is always same. So these are in series, and these are formed by, these are, or in other words, this is formed by combination of these two. That means if 1.25 amperes is going through this one will also have 1.2 amperes, 1.25 amperes. Okay, same current will appear in the constituent resistors. Now we know R and A, or R and I. If we know R and I, we can also find delta V. So delta V here would be using the Ohm's law. Ohm's law is delta V is equal to I times R. So I is 1.25, R is 10. So multiplying those two, you get 12.5 volts. Okay. Likewise, we can get delta V across this resistor. I times R, 1.6 times 1.25. 1.6 times 1.25, that gives us 2. Volts. Okay. Now go further back. So this one, delta V is 12.5 volts and current is 1.2 amperes, 25 amperes. Okay, so this is not changed, it's still 10 ohms here. So delta V and I would be just like in this one. But now here, these two are combined to form that. Okay, so these two are combined to form that. And these two are in parallel. So when the two parallel combine to form a resistor, the potential difference across the combined one would also be same for the potential difference across the individual ones. So the potential difference here is 2 volts. Same potential difference would also appear on each of these ones. So this will have 2 volts and this will also have 2 volts. Okay. So that means if we know V and R, I can find I. So using this formula, so I is delta V over R. Okay, so delta V is 2 and R is 8. So doing the math, is it 0.25? 2 divided by 8, 0.25 amperes. Likewise, we can also find I here. So I would be delta V is 2, and then R 5 is 2 ohms, which is given here. So that is 1 ampere. Okay. And then last, we can go back to this step now. Okay. So let's go back to this step. Now we got the current and potential difference for this one, okay, I5, and then the current through this one is 0.25 amperes, and this one is the combination of these two in series. Okay, so that means the current through this one would also be the current through each of these ones. Okay, so the current here would be 0.25 and 0.25. Same thing with this one. So this is the combination of these two in series. So the current through this one would also be current through each of these ones. So here current would be 1.25, current here would be 1.25 amperes. So then we can find delta V for each of the resistors. So delta V would be I over I times R. So I is 1.25, R is 6. So multiplying 1.25 times 6 gives me 7.5 volts. Here I is 1.25, R2 is 4, that gives me 5. Here I is 0.25, R3 is 5, that gives me 1.25 volts, and then I here is 0.25 times R4 is 3, that gives me 0.75 volt. Okay, so this one we already found, I5, which is 1 ampere and 2 volts. So now we have current and voltage for all the resistors. Okay, so that's the current and voltage for this one, current and voltage for I2, current and voltage for the third one, current and voltage for the fourth one, current and voltage for the fifth one. Okay, that's part B. Any question on this one? So the only idea that you need to keep in mind to do these kinds of problem is, let me tell you what you need to know. So if you are combining two resistors in parallel, okay, you combine these two to 1. Okay, so delta V in this one would be also delta V on this one and delta V on that one. Okay, so that's one thing. And the other one is, if you're combining two resistors in series, combining these two to get this equivalent resistor. Let's say that's R1 and R2. So the current through this one would be current through that one and current through that one. Okay. So that's all you need to know. And then you need to know delta V is I times R. So that's the rule to do the problem. I don't know why it's doing that. Okay. Any question? So this number 2, we will do this on in lab today. I will record that and then you can watch that later. So the next thing is, sometimes we may see the problems that could not be solved by just using the Ohm's law and just using the combination, the series and parallel combination. Okay, we may need to use something, a rule called Kirchhoff's rule. Okay, so this is a rule that could be used to solve complex problems, complex circuit problems. What is Kirchhoff's rules? Kirchhoff's rules. There are two Kirchhoff's rules. One is, let's say there are a bunch of currents, let's say I1, I2, I3, I4, okay, and I5. They are all meeting at a junction, so that's the junction. And if they are meeting at the junction, the rule is, at that junction the sum of the currents would be 0. Okay, with the convention that current in, we can use positive sign for that, and current out, a negative sign for that. Okay, so at junction, I1, I2, I3, I4, I5, the net current would be 0. With the sign I in is positive, so I1 is positive, it's going in. I2 is also positive, going in. I3 is coming out, negative. I4 is coming out, negative. I5 is also coming out, negative. Okay, so that's junction rule. It's called junction rule, Kirchhoff's junction rule. That's the first rule. Second rule is called loop rule. So another easier way to, before we move on to loop rule, another one easier way to remember this, if you don't want to remember this sign convention, okay, if you hate remembering the things, what you can do is, you can just say current, total current in is equal to total current out. Okay, you can just say that. So total current in is, in this case, I1 plus I2 is total current in, that is equal to total current out, I3 plus I4 plus I5. Okay, so you can either use that or use that, whichever you want. Both will give the same result. Okay, loop rule. So let's say you have a loop with some components like resistor and battery, and then more than one resistor, let's say another resistor here, and let's say another battery here. Okay, so this one is electromotive force 1 or potential difference 1, potential difference 2, call this R2, and let's say the current flowing through this entire circuit is I. Okay, because it's in everything is in series, so the total current is I, same everywhere. So according to loop rule, the potential, or I should say sum of potential difference or a difference along a loop is 0. Okay, in other words, the sum of potential difference in this entire loop is 0. So what that means is, so this longer line is positive, okay, longer line of the battery is positive, and shorter line is negative. Shorter line is negative. Now let's say the current is going in clockwise direction. Okay. Now imagine that you are sliding downhill. So this sliding will work only if this is at higher potential and this is at lower potential, and you always slide down from higher to lower potential. Okay, so in this case also, current flows only if there is higher and lower potential. Current always flows from higher potential, which we call positive, to the lower potential, which is negative. Okay, so imagine there is current flow. If it is like this, okay, then current won't flow from lower to higher. Okay, so if your slide is here, then you won't go up naturally. It's not possible. You cannot go from lower potential to higher potential naturally without using any external aid. Okay, or if the potential is same, if you have same potential and then you are on a slide or something, you won't be able to slide along this path. Okay, it will just remain as it is. So in order to move down the hill, one point needs to be at higher potential and other point needs to be at lower potential, and your motion is always from higher to lower. Okay, so motion is from positive to negative, or higher potential to lower potential. That's the basic idea. Same kind of idea applies here, so let's apply that. So the current is flowing from this left to right along this resistor. That means this must be positive, higher potential, and this must be lower potential, because current is going along that direction. Likewise, in this one, current is going along this direction. You look at that current. It's going from right to left. That means this must be higher potential and that must be lower potential. Okay, again, current always flows from higher potential to lower potential, just like when you move down the hill. Okay, so with that, now we can apply this. So start with any component. Let's say, let's do this. Let's look at this component R2. What's the potential difference across that? Potential difference is I times R. Okay. So what is I through that? I is just I. Okay. That I is going through that. And then what is R? That's R2. Okay. So we are going from, let's choose a path. Let's say we are going along this counterclockwise path. So going from positive to negative, what happens to the potential. This is the potential across that resistor. So when you go from higher potential to lower potential, what happens to the potential? In other words, if you go from higher potential energy to lower potential energy, what happens to your potential energy? Do you lose potential energy or gain potential energy? Lose potential energy, yeah. So going from higher potential energy, meaning let's say your potential energy is 100 here. Here you will have 0 potential energy, right? So you are losing the potential energy from 100 to 0. Whenever you are losing something, you always use negative sign. For example, if you have like, this is the example I usually give. So you have $100 to begin with. You lost all the money and your final is 0. Okay, so final minus initial. Final is 0, initial is 100. So your lost amount is minus $100, right? So whenever you lose something, you always have negative sign, okay, for the net. So same thing here. So going from higher potential to lower potential, you are losing the potential. So that's the negative sign, okay, for the lost potential. And then when you go from this point to that point, we are just choosing a line or path. So going from negative to positive, we are going from lower potential to higher potential. That means you are gaining the potential. Okay, you are climbing the hill. From lower potential to higher potential, you gain the potential, so it's positive. And the potential gain here is E2. And then the next component is this one. So again, going along this path, okay, counterclockwise, going from negative to positive to negative, higher to lower potential, that's negative. Potential here in this component is IR1. And then the last one is this one. So in this one, we are going from higher to lower. Higher to lower is again negative. Okay, so that's the Kirchhoff's rule. So the main idea here is going from positive to negative or higher potential to lower potential. Delta V would have negative sign. Going from negative to positive or lower potential to higher potential, delta V would be positive. Okay. That's what you need to remember. So let's apply this to a problem. So let's see this problem. That will make the things a little bit easier to conceptualize. So basically you need to use Kirchhoff's rule in this problem to find the potential difference across each resistor. Let's see. Yeah, so this is actually V, sorry, there is a typo, that's the EMF. So you need to find delta V for this resistor, let's call that delta V1, and you need to find delta V for this resistor, call that delta V2, and then you also need to find I. Okay. So first step to use Kirchhoff's rule, this is the loop rule. There's no junction here, so we don't need to use junction rule. So we want to use loop rule. The first rule is assign the signs of the components. So the rule here is longer line for battery is positive, shorter line is negative. Longer line is positive, shorter line is negative, first step. Second step is look at the direction of the current. So current is flowing this clockwise direction, in clockwise direction. Just by looking this current, you can say it's going like this, okay, in clockwise direction. Now, the entering point of the current in the resistor is higher potential. The exit point is lower potential or negative. Okay, positive is higher potential, negative is lower potential. Positive is entry point of the current, and negative is exit point of the current. Okay, so this is entry point, current is going first through that point, so that's positive, that's negative. And here, this is the entry point, current goes through that first, so that's positive. And exit point is that current comes out from there, so that's negative. Okay, so that's the first thing you need to do. And the second thing is choose a path, okay, either clockwise path or counterclockwise path, doesn't matter. So let's choose a clockwise path, okay, so just choose a either clockwise or counterclockwise, doesn't matter. Let's say counterclockwise, clockwise. Okay, so I'm choosing a clockwise path, and then just follow that path. Follow that path means choose a component out of 4, just choose one, and then follow the path, and then add the potential difference across each of the components. So let's say start with that one. Okay, so we are choosing clockwise path, so going this way along clockwise direction. That means we are going from higher potential to lower potential. So going from higher to lower potential, the potential difference decreases. Okay, the idea here is from higher to lower is negative sign, and lower to higher, delta V is positive sign. So we are going from positive to negative, higher to lower. So delta V would be 9 volts and minus, decrease in potential difference. And then going along the path clockwise, the next component is this one. Potential difference here would be I times R. I is just I. Okay, I is same everywhere. Here is I everywhere same. And then the R here is 20 ohms. And we are going from positive to negative. Positive to negative is negative sign. Okay. Next component along that line, along that path is this one. We are going from negative to positive. Okay, going clockwise. It's going from negative to positive. Sign would be positive here, 6 volts. And in the next one, current here is I. Potential difference is 40 ohms. Okay, and then we are going from positive to negative. Okay, from here to here. That means positive to negative is negative, and sum of all those potential differences is 0. Okay, so add this one and this one, so that's minus 9 and 6 is minus 3, and this one is negative 20i, negative 20i, and this is negative 40i is equal to 0. So negative 3i is equal to, no, negative 3 is equal to 60i. Okay, so I is negative 3 over 60, so that would be negative 3 over 60. 0.05 amperes. Okay, that's the current. And then you can, once you have current, you can use this Ohm's law to find delta V. So 0.05 times 20 ohm, that's 0.05 times 40 ohms. So that gives you delta V. Okay. We'll do more complex problems, and then where we will use the loop rule with the junction rule. next time. Okay, so we'll continue this next time. If you have any question, I can answer your question. Otherwise, it matters. I will explain about the sign next time. So what that means. Okay. So we have this negative sign. What is meant by that negative sign? So we'll talk about that next time. It matters. Okay.